The oil pump in an internal combustion engine circulates engine oil under pressure to the rotating bearings, the sliding pistons and the camshaft of the engine. This lubricates the bearings, allows the use of higher capacity fluid bearings and also assists in cooling the engine. As well as its primary purpose for lubrication, pressurized oil is increasingly used as a hydraulic fluid to power small actuators. One of the first notable uses in this way was for hydraulic tappets in camshaft and valve actuation. Increasingly common recent uses may include the tension nerve for a timing belt or variators for variable valve timing systems. Pumps. The type of pump used varies. Gear pumps, trichoid pumps and vane pumps are all commonly used. Plunger pumps have been used in the past, but these are now only used rarely, for small engines. To avoid the need for priming, the pump is always mounted low down, either submerged or around the level of the oil in the sump. A short pickup pipe with a simple wire mesh strainer reaches to the bottom of the sump. Pump drive. For simplicity and reliability, mechanical pumps are used, driven by mechanical gart drains from the crankshaft. Reducing pump speed is beneficial, and so it is usual to drive the pump from the cam or distributor shaft, which turns at half engine speed. Placing the oil pump low down uses a near vertical drive shaft, driven by helical skew gears from the camshaft. Some engines, such as the Fiat twin-cam engine of 1964, began as OHV engines with an oil pump driven from a conventional camshaft in the cylinder block. When the twin overhead cam engine was developed, the previous oil pump arrangement was retained and the camshaft became a shortened stub shaft. Even when the distributor position was moved from the previous block mount to being mounted on the cylinder head camshafts, the oil pump drive remained in the same position, the unused distributor position now covered by a blanking plate. Small engines, or scooters, may have internal gear pumps mounted directly on their crankshaft. For reliability, it is rare to use an external drive mechanism, either a separate belt drive or external gears, although camshaft-driven pumps often rely on the same timing belt. Additional separate belts are sometimes used where dry sump pumps have been added to engines during tuning. Electric oil pumps are not used, again for reliability. Some turbo-time or electric auxiliary oil pumps are sometimes fitted to turbocharged engines. These are a second oil pump that continues to run after the engine has stopped, providing cooling oil to the hot bearings of a turbocharger for some minutes, whilst it cools down. These are supplementary pumps and do not replace the main, mechanical, oil pump. Lubricating system. The oiling system addresses the need to properly lubricate an engine when Euro unregistered trademark S running. Properly lubricating an engine not only reduces friction between moving parts but is also the main method by which heat is removed from pistons, bearings, and shafts. Failing to properly lubricate an engine will result in engine failure. The oil pump forces the motor oil through the passages in the engine to properly distribute oil to different engine components. In a common oiling system, oil is drawn out of the oil sump through a wire mesh strainer that removes some of the larger pieces of debris from the oil. The flow made by the oil pump allows the oil to be distributed around the engine. In this system, oil flows through an oil filter and sometimes an oil cooler, before going through the engine Euro unregistered trademark S oil passages and being dispersed to lubricate pistons, rings, springs, valve stems, and more. Oil pressure. The oil pressure generated in most engines should be about 10 psi per every 1,000 revolutions per minute, peaking around 55 to 65 psi. Local pressure is far higher than the 50, 60 psi and C set by the pumper Euro unregistered trademark S relief valve, and will reach hundreds of psi. This higher pressure is developed by the relative speeds in feet per second of the crankshaft journal itself against the bearing width, oil viscosity, and temperature, balanced against the bearing clearance. All pump pressure dose is a Euro fill in the Euro and refresh the oil in the annular space faster than the leak expels it. This is why low-speed engines have relatively large journals, with only modest pump size and pressure. Low pressure indicates that leakage from the bearings is higher than the pumper Euro unregistered trademark S delivery rate. Gauge pressure. The oil pressure at the pump outlet, which is what opens the pressure relief valve, is simply the resistance to flow caused by the bearing clearances and restrictions. The oil pressure gauge, or warning lamp, gives only the pressure at the point where its sender enters that part of the pressurized system, not everywhere, not an average, nor a generalized picture of the systemic pressure. Despite the frequent comparison to hydraulic engineering theory, this is not a OE closed system in which oil pressure is balanced and identical everywhere. All engines are OE open systems because the oil returns to the pan by a series of controlled leaks. The bearings farthest from the pump always have the lowest pressure because of the number of leaks between the pump and that bearing. Excess bearing clearance increases the pressure loss between the first and last bearing in a series. Depending on condition, an engine may have acceptable gauge pressure, and still only 5 psi pressure at one connecting rod, which will fail under high load. The pressure is actually created by the resistance to the flow of the oil around the engine. So, the pressure of the oil may vary during operation, with temperature, engine speed, and wear on the engine. Colder oil temperature can cause higher pressure, as the oil is thicker, while higher engine speeds cause the pump to run faster and push more oil through the engine. Because of variances in temperature and normal higher engine speed upon cold engine startup, ETA-1 registered trademark S normal to see higher oil pressure upon engine startup than at normal operating temperatures, where normal oil pressure usually falls between 30 and 45 psi. Too much oil pressure can create unnecessary work for the engine and even add air into the system. To ensure that the oil pressure does not exceed the rated maximum, once pressure exceeds a preset limit, a spring-loaded pressure relief valve dumps excess pressure either to the suction side of the pump, or directly back to the oil pan or tank. High oil pressure frequently means extremely high pressure on cold startup, but this is a design flaw rather than an automatic consequence of high pressure. The observation if you raise the maximum pressure, the cold pressure goes too high is accurate, but not intentional. Even the stock pumps do not have enough relief valve capacity, the relief port is too small to handle the volume of cold oil. This is why there is a significant difference between cold and hot oil, high and low RPM, and C, but ETA-1 registered trademark S typically not a problem with stock engines. A correctly designed relief port will flow any oil volume the gears will pass, regardless of oil viscosity or temperature, and the gauge reading will only vary slightly. The oil pressure is monitored by an oil pressure sending unit, usually mounted to the block of the engine. This can either be a spring-loaded pressure sensor or an electronic pressure sensor, depending on the type of sending unit. Problems with the oil pressure sending unit or the connections between it and the driver's display can cause abnormal oil pressure readings when oil pressure is perfectly acceptable. Low oil pressure, however, can cause engine damage. Low oil pressure can be caused by many things, such as a faulty oil pump, a clogged oil pickup screen, excessive wear on high-mileage engines, or simply low oil volume. Indications of low oil pressure may be that the warning light is on, a low pressure reading on the gauge, or clattering clinking noises from the engine. Low oil pressure is a problem that must be addressed immediately to prevent serious damage. The leading cause of low oil pressure in an engine is wear on the engine ETA-1 registered trademark S vital parts. Over time, engine bearings and seals suffer from wear and tear. Wear can cause these parts to eventually lose their original dimensions, and this increased clearance allows for a greater volume of oil to flow over time, which can greatly reduce oil pressure. For instance, 0.001 of an inch worn off of the engine ETA-1 registered trademark S main bearings can cause up to a 20% loss in oil pressure. Simply replacing worn bearings may fix this problem, but in older engines with a lot of wear not much can be done besides completely overhauling the engine. Particles in the oil can also cause serious problems with oil pressure. After oil flows through the engine, it returns to the oil pan, and can carry along a lot of debris. The debris can cause problems with the oil pickup screen and the oil pump itself. The holes in the oil pickup screen measure about 0.04 square inches. Holes of this size only pick up bigger pieces of debris and allow a lot of smaller pieces to flow through it. The holes in the screen are so big because at low temperatures and slow engine speed the oil is very viscous and needs large openings to flow freely. Even with these large holes in the screen, it can still become clogged and cause low oil pressure. A 0.005-inch thick coating on the screen can reduce hole size to about 0.03 square inches, which in turn reduces the flow of oil by 44%. Even after passing through the oil pickup screen and the oil filter, debris can remain in the oil. It is very important to change the oil and oil filter to minimize the amount of debris flowing through your engine. This harmful debris along with normal engine wear in high-mileage engines causes an increase in clearances between bearings and other moving parts. Low oil pressure may be simply because there is not enough oil in the sump, due to burning oil or leakage. The piston rings serve to seal the combustion chamber, as well as remove oil from the internal walls of the cylinder. However, when they wear, their effectiveness drops, which leaves oil on the cylinder walls during combustion. In some engines, burning a small amount of oil is normal and should not Euro 1 registered trademark T necessarily cause any alarm, whereas burning lots of oil is a sign that the engine might be in need of an overhaul. Oil pumps in high-performance engines. Not all engines have the same oiling needs. High-performance engines, for example, place higher stress on the lubricating system. In this case, the lubricating system must be especially robust to prevent engine damage. Most engines in cars on the road today don't near Euro 1 registered trademark T run much past 5,000 to Euro 6,000 RPMs, but that isn't a Euro 1 registered trademark T always the case in performance engines, where engine speeds could reach up to 8,000 to 9,000 RPMs. In engines like these, it is imperative that the oil circulates quickly enough, or air may become trapped in the oil. Also, to free up power, some engines in performance applications run lower weight oil, which requires less power to run the oil pump. Common oil weights in engines today are usually either 5W30 or 10W30 oil, whereas performance engines might use 0W20 oil, which is less viscous. Wet and dry sump systems. Conventional wet sump engines have one oil pump. It is generally located inside the lower part of the engine, usually below and or to one side of the crankshaft. On dry sump engines, at least two oil pumps are required, one to pressurize and distribute the oil around the engine components, and at least one other scavenge pump to evacuate the oil which is pooled at the bottom of the engine. This scavenge pump is sometimes located in the sump of the engine, and crucially, this scavenge pump's flow rate capacity must exceed that of the pump which pressurizes and distributes oil throughout the engine. Because of the dry sump's external oil reservoir, excess air can escape the oil before the oil is pumped back through the engine. Dry sumps also allow for more power because they reduce the amount of windage, oil sloshing up into the rotating assembly, and the vacuum from the scavenge pump improves ring seal. Dry sumps are more popular in racing applications because of the improved power and reduced oil sloshing that would otherwise reduce oil pressure. Disadvantages of dry sumps are increased weight, additional parts, and more chances for leaks and problems to occur. See also, ring oiler, references. External links, engine failure,